Single variable calculus. AP Calculus AB, BC, pacing. Single variable calculus, limits intuition. For pacing, it is 1 out of 18. What is the slope at a point on a curve f of x? What is the area under f of x? Derivative, slope, integrals, area. To find the slopes of tangent lines on curves, note that the slope of the secant lines approach the slope of the tangent lines. To find the areas underneath functions, note that the area of the rectangles approach the area of the trapezoid when we have many thin rectangles. Both slopes and areas depend on approaching, that is, limits. Absolute value x for x not equal to 0, absolute value x for x not equal to 0, 0.5 for x equals 0. What do the values of f of x approach as x approaches 0? These f of x values approach 0 as x approaches 0 on either side, but x is not equal to 0. Visually, we can consider arrows that trace the curve on either side, or a red box of decreasing height and the blue box of decreasing width. The f of x values approach 0 as x approaches 0 on either side, but x is not equal to 0. Limit as x approaches 0 of f of x equals 0. Note how limits could exist in general. Limit as x approaches a of f of x equals f of a. Limit as x approaches a of f of x exists, but f of a does not exist. Limit as x approaches a of f of x does not equal f of a. Consider limit as x approaches a of f of x as a double-sided limit here, where both limit as x approaches a from the positive, f of x, approaching a from the right, equals limit as x approaches a from the minus f of x, approaching a from the left. F of x equals absolute value x over x, which equals this. What do the values of f of x approach as x approaches 0? As x approaches 0, the f of x values approach minus 1 from the left, but 1 from the right. The limit as x approaches 0 from the negative f of x equals minus 1 does not equal limit as x approaches 0 from the positive f of x equals 1. The f of x values don't approach any one number as x approaches 0 from either side. The red box cannot decrease in height as blue decreases in width. The double-sided limit does not exist, but each one-sided does exist. Limits. Limit as x approaches a of f of x equals L if and only if limit as x approaches a from the minus f of x equals L equals limit as x approaches a from the positive f of x. The intuitive idea of the limit is that we can make the values of f of x as close to L as we like by making x close enough on either side of a, but x is not equal to a. We say the limit of f of x as x approaches a equals L. If the limit is one-sided, then we say left-hand limit or right-hand limit. Algebraically, we can show that limit as x approaches 0, absolute value x equals 0. We start with the function, make it piecewise, and show that both the left and right limits are equal. limit as x approaches 0, absolute value x, and recall that absolute value x equals this. Limit as x approaches 0 from the negative absolute value x equals limit as x approaches 0 from the negative minus x equals 0 equals limit as x approaches 0 from the positive absolute value x equals limit as x approaches 0 from the positive x equals 0. Algebraically, we can show that limit as x approaches 0, absolute value of x over x does not exist. We start with the function, make it piecewise, and show that the left and right limits are not equal. Limit x as it approaches 0, absolute value x over x, and note that absolute value x over x equals this. Limit x approaches 0 from the negative, absolute value x over x, equals limit as x approaches 0 from the negative minus 1 equals minus 1, does not equal limit as x approaches 0 from the positive, absolute value x over x, equals limit as x approaches 0 from the positive 1 equals 1. Limits. Nuance. Note that two functions could not have limits, but their sum could. For example, here. So be careful when it comes to combinations of functions and intuitive limits. Below, see what happens to the values of f of x as x approaches 0. The arrows wouldn't approach the same value. The red box couldn't get short. The limit does not exist when f of x does not approach a number L, no matter how close x is on either side. No two-sided limit, oscillation, and plus and minus infinity. But we can use the notation of limits with the infinity sign. Asymptotes. Consider the various combinations of limit as x approaches a f of x equals L, both two- and one-sided, if a and or L would be either positive or minus infinity. Vertical and horizontal asymptotes. Vertical asymptotes, x equals a, are when f of x approaches positive or minus infinity as x approaches a in some way, often when a non-zero is divided by a 0. Horizontal asymptotes y equals L are when f of x approaches L as x approaches positive infinity or minus infinity. 1 over x, 1 over x squared, x cubed, minus x to the power 3. Various limits. f1, f2 have a vertical asymptote at x equals 0. f1, f2 have a horizontal asymptote at y equals 0. Ln x, e to the x, tangent x, arctan x. Various limits. f3 has a vertical asymptote at x equals 0. f4 has both at x equals minus pi over 2 and x equals pi over 2. f5 has a horizontal asymptote at y equals 0, and f6 has both at y equals minus pi over 2 and y equals pi over 2. Algebraically, we can show that limit as x approaches 0, 1 over x does not exist, and limit as x approaches 0, 1 over x squared equals infinity. We start by finding the left and right side limits and see if they're equal. Note that pos means tiny positive and neg means tiny negative. Limit as x approaches 0 from the minus 1 over x equals 1 over neg equals minus infinity does not equal limit as x approaches 0 from the positive 1 over x equals 1 over pos equals positive infinity. Limit x approaches 0 from the negative 1 over x squared equals 1 over neg squared equals 1 over pos equals positive infinity equals limit as x approaches 0 from the positive 1 over x squared equals 1 over pos squared equals positive infinity. Algebraically, we can find the first positive vertical asymptote of tangent x with tangent equals sine over cosine being non-zero over 0, which is visually this. Note that cosine x equals 0 when x equals pi over 2 plus n pi, and sine x equals 0 when x equals n pi. We have the following. So x equals pi over 2 is the first positive vertical asymptote of tangent x. Rational-ish functions. To find the asymptotes of rational functions, technically we divide all terms by the highest power in the denominator and evaluate the limits. For us, we use the ratio of the terms with the highest exponents, since they matter more than the other terms. Pos means huge positive. We have the following. First case. Generally, the limits as x approaches infinity or x approaches minus infinity may differ due to coefficients exponents. Second and third cases, the limits are the same as x approaches positive or minus infinity. With radicals, the terms with the highest exponents still matter the most, but we might have different limits as x approaches infinity or x approaches minus infinity. We have the following. Algebraically, we can show that limit as x approaches 0 arctan 1 over x does not exist. We start by finding the left and right side limits and see if they're equal. We need a substitution to make our composite function into a simple one. Let t equal 1 over x. As x approaches 0 from the negative, then t approaches negative infinity. And as x approaches 0 from the positive, then t approaches infinity. Limit as x approaches 0 from the negative, arctan of 1 over x becomes limit as t approaches minus infinity of arctan t equals negative pi over 2. Does not equal limit as x approaches 0 from the positive arctan of 1 over x, which becomes limit as t approaches infinity arctan of t equals pi over 2. Algebraically, we can show that limit as x approaches 0 of arctan of 1 over x squared equals pi over 2. We start by finding the left and right side limits and see if they're equal. We need a substitution to make our composite function into a simple one. Let t equal 1 over x squared. As x approaches 0 from the negative, then t approaches infinity. And as x approaches 0 from the positive, then t approaches infinity. Limit as x approaches 0 from the negative, arctan of 1 over x squared becomes limit as t approaches infinity, arctan of t equals pi over 2 equals limit as x approaches 0 from the positive, arctan of 1 over x squared becomes limit as t approaches infinity, arctan of t equals pi over 2. For one-sided limits, like limit as x approaches infinity of sine 1 over x, limit as x approaches minus infinity sine 1 over x, and limit as x approaches 0 from the negative of e to the 1 over x. Be careful with how we approach. Below, with t equals 1 over x, note that we need positives or negatives when t approaches 0. When x approaches infinity, then t approaches 0 from the positive, and when x approaches minus infinity, then t approaches 0 from the negative. When x approaches 0 from the negative, then t approaches minus infinity. Limit as x approaches infinity sine 1 over x becomes limit as t approaches 0 from the positive sine of t equals 0. Limit as x approaches minus infinity sine 1 over x becomes limit as t approaches 0 from the negative sine of t equals 0. Limit as x approaches 0 from the negative e to the 1 over x becomes limit t approaches minus infinity e to the t equals 0. We can find limit x approaches infinity x squared minus x, but we cannot substitute positive or minus infinity. We need to manipulate, factor, make into a fraction, etc., and consider pos, huge positive, and neg, huge negative. Limit x approaches infinity x squared minus x equals limit x approaches infinity x minus 1 equals pos times pos equals infinity. Or we could have this. We can show that limit x approaches infinity sine x or limit x approaches minus infinity sine x does not exist. The values oscillate between minus 1 and 1 infinitely often and don't approach any definite number. Single variable calculus limits calculations. In terms of pacing, this is 2 out of 18. For x approaches a, f of x, when we evaluate f of a, we get the following situations. Non-zero over non-zero, which equals a non-zero. A 0 over non-zero, which equals a 0. A non-zero over 0, which is an asymptote. When we have the 0 over 0 situation, we have to use intuitive limit laws to manipulate our function into an equivalent form that doesn't have that division issue. F of x equals f of g, where x doesn't equal a, then limit as x approaches a of f of x equals limit as x approaches a of g of x. Since limits don't consider what actually happens at a, we bypass our original division issues. We can compute limit x approaches 1, x squared minus 1 over x minus 1, limit x approaches 0, square root x plus 1 minus square root 1 over x, and limit x approaches 0, 2 sine x over sine 2x, using factoring, conjugates, and trigonometric identities, respectively. We have the following. Often, we consider factoring expanding, usually with polynomials, and conjugates, usually with radicals. Calculate limit x approaches infinity, square root x squared plus 1 minus x using conjugates. We cannot substitute infinity. We have the following. What is a number x that is or at least 5 and that is or at most 5? The number x is squeezed between 5s, and so x equals 5. The idea of squeeze theorem is if f of x less than or equal to g of x less than or equal to h of x, and limit as x approaches a of f of x equals L equals limit as x approaches a of h of x, then limit as x approaches a of g of x equals L. Compute limit x approaches 0 x squared sine 1 over x by first noting negative x squared less than or equal to x squared sine 1 over x less than or equal to x squared, and using squeeze theorem. Here is a picture. Start with sine x, which is between its range. A different input does not affect range. Multiply by x squared. Take the limit as x approaches 0 on its ends. Evaluate limits on the ends. Applies the squeeze theorem. Compute limit theta goes to 0, sine theta over theta, by using some geometry and squeeze theorem. Here's a picture. Start with small theta. Arc AB equals theta. Length BC equals sine theta. Length AD equals tan theta. Divide by sine theta. Reciprocate each term and flip inequalities. Take limit as theta approaches 0 positive on the ends. Evaluate limits. Sine theta over theta is an even function, and squeeze theorem. Compute limit theta goes to 0 cosine theta minus 1 over theta by using conjugates, trigonometric identities, and using our previously solved limits. We have the following. We can compute limit x goes to 0 sine 3x over 4x, limit x goes to 0 x cotan x, and limit theta goes to 0 cosine theta minus 1 over sine theta. We have the following. Note, for the first limit, if theta equals 3x, then as x goes to 0, theta goes to 0. Continuity. A function f is continuous at a point a if limit as x approaches a of f of x equals f of a. Visually, this means the graph of f has no holes or breaks. There's also continuity from the left and right that used one-side limits. We can show that f of x equals absolute value x is continuous at x equals 0, since limit as x approaches 0 of absolute value x equals 0 equals absolute value 0. A function being continuous is different from being continuous on an interval. Continuous functions are continuous at every point in their domain. Continuity on an interval means continuous at every point in the interval. So, for example, 1 over x is a continuous function since it's continuous on its domain, x not equal to 0, but it is not continuous on intervals with x equals 0. If f is continuous at b and limit x approaches a g of x equals b, then limit x approaches a f of g of x equals f of b. And we have the following. This means that we can find limits inside of continuous functions. We can calculate limit as x approaches 1, arc sine of this. We have the following. Discontinuity. If f is not continuous at a point a, then it is discontinuous at a. Limit as x approaches a, f of x does not equal f of a. All these functions are discontinuous on intervals with x equals 0. Respectively, these discontinuities are removable, a point, jump a step, oscillating, and infinite. Intermediate value theorem. A tree grows from 1 meter to 2 meters in a year. Sometime in that year, the tree was 1.5 meters. Intermediate value theorem. A function that is continuous on the closed interval ab has a c in open interval ab such that f of c is between f of a and f of b. Visually, the graph of a continuous function takes every x and y coordinate between the x and y coordinates of its endpoints. For example, we can prove that f of x equals x has a root. Note that x is continuous because it's a polynomial on interval -1 to 1, and f of -1 equals -1, and f of 1 equals 1. And so, by the intermediate value theorem, f of x equals 0 somewhere on -1 to 1. Single variable calculus, differentiation, intuition and calculations. In terms of pacing, this is 3 out of 18. What is the slope of line? It's the same wherever on the line. What is the slope of a curve? It depends where we are on the curve. The slope of a curve is really the slope of the tangent line to a point on the curve. Here is a picture. The slope of the blue secant line approximates the slope of the red tangent line. The approximations get better as x approaches a. Think limit. Note x equals a yields 0 over 0. The tangent line to f of x at x equals a is the line through the point with slope m. M equals f prime of a equals limit as x approaches a, f of x minus f of a all over x minus a equals limit as h approaches 0, f of a plus h minus f of a over h. Here is the tangent line of f of x equals x squared at point where x equals a. We have the following. When x equals a equals 1, the slope is 2. The tangent line to x squared at 1, 1 is y minus 1 equals 2x minus 1, or y equals 2x minus 1. The derivative of a function f at x equals a is f prime of a equals limit as x approaches a, f of x minus f of a over x minus a equals limit h approaches 0, f of a plus h minus f of a over h if x equals a plus h. This function is differentiable at a if f prime of a exists. The tangent line to f of x at x equals a is the line y minus f of a equals f prime of a, which equals m, x minus a. Parallel lines have the same slope m. Normal lines have the slope minus 1 over m. We differentiate the function f of x equals x squared to find its derivative, f prime of x equals 2x. The average rate of change of y equals f of x with respect to x over the interval x1 to x2 is delta y over delta x equals f of x2 minus f of x1 all over x2 minus x1, which is the difference quotient and can be interpreted as the slope of the secant line that connects x1 f of x1 and x2 f of x2. The instantaneous rate of change of y equals f of x with respect to x at x equals x1 is limit as delta x goes to 0, delta y over delta x equals limit as x2 approaches x1, f of x2 minus f of x1 over x2 minus x1, which is the derivative f prime of x1 and can be interpreted as the slope of the tangent line at x1, f of x1. Notations that we'll use are f prime of x equals y prime equals dy dx. If we want to take the derivative and evaluate at a, then f prime of a dy dx x equals a, dy dx x equals a. The derivative of the first derivative is the second derivative. F double prime of x and higher derivatives, the nth derivative at x here is a picture. The differential dx is how much x changes. The differential dy is how much the tangent line rises or falls by dx. Dy equals f prime of x dx. In contrast, how much the function rises or falls by delta x is delta y equals f of x plus delta x minus f of x. As an example, let f of x equal x squared, with f prime of x equals 2x, and consider a equals 1. And so f of 1 equals 1, f prime of 1 equals 2. From here, we can find the following equations. Tangent line, linear approximation, linearization. If we had dx equals delta x equals 0.5 and x equals 1, then we could find change in tangent line, change in function. So the linear approximation for x squared centered at x equals 1 will give L of 1.5 equals 2. Where derivatives exist, the functions look locally linear. Derivatives do not exist, DNE, with discontinuity, corners, cusps, vertical tangents, and oscillations, since they do not become locally linear. None of these functions have derivatives at x equals 0, so no tangent lines there. If f is differentiable at a, then f is continuous at a. But the converse, which is if f is continuous at a, then f is differentiable at a, is not true. Nuance. Although a derivative might not exist at a point, it might exist at other places. Consider f of x equals absolute value x, and how geometrically f prime of x equals this. Note that two functions could be non-differentiable at a, but combinations of them could be differentiable at a. Consider adding a positive and negative absolute value to get the horizontal line y equals 0, with the slope y prime equals 0. Although each individual function wouldn't have a derivative at x equals 0, the sum y equals 0 does. Basic derivative rules. Constant multiple, sum and difference, product rule, quotient rule, chain rule. Derivative rules. The derivative of x to the power n equals n x to the power of n minus 1. The derivative of a constant is 0. The derivative of a constant times a function is that constant multiplied by the derivative of that function. We need to manipulate our function so that the rules apply. Also simplify. Find the derivatives of x squared root x square root x square root x, and 1. And we have the following. Find the derivatives of 1 over square root x, 1 over x, 1 over x square root x, 1 over x squared. Find the derivatives of 10x squared over 11, 10x square root x over 9, 8x over 9, 8 square root x over 7, 6 over 7. Find the derivatives of 6 over 5 square root x, 4 over 5x, 4 over 3x square root x, 2 over 3x squared. Differentiate f of x equals x squared e to the x and g of x equals e to the x over x squared. Note that we can't manipulate. Recall product rule. Fg prime equals f prime g plus fg prime, and quotient rule. F over g prime equals f prime g minus fg prime over g squared. We have the following. Sometimes, if we can manipulate, we can bypass product or quotient rule. Consider this. Y equals t cubed x to the power 5 plus t to the power 7 x to the power 9. To find dy d whatever, we treat only whatever as a variable and everything else as a constant. And we have the following. Single variable calculus, differentiation, chain rule. In terms of pacing, this is 4 out of 18. How much faster is a second compared to an hour? How much faster is a second compared to a day? Here is the following. The idea. To find the derivative of the double composite function, consider f of x equals f of g of x becomes f of g where g equals g of x. And the derivative df dx equals df dg dg dx equals f prime of g, g prime of x, f prime g of x, g prime of x. In words, the derivative of the outer function with input of the inner function multiplied by the derivative of the inner function. Find the derivative of f of x equals f of g of x equals sine squared of x, which equals sine x squared. We have the following, and we have the following. Find the derivative of f of x equals f of g of x equals sine of x squared. We have the following, and then we have the following. The idea. To find the derivative of the triple composite function, consider f of x equals f of g of h of x becomes f equals f of g, and g equals g of h, and h equals h of x. And the derivative df dx equals df dg, dg dh, dh dx. F prime of g, g prime of h, h prime of x. F prime of g of h of x, g prime of h of x, h prime of x. Note how we chain the derivatives together, which, after simplification, we get the derivative of f with respect to x. Find the derivative of f of x equals f of g of h of x equals sine of cosine of tangent. We have the following and the following. Find the derivative of f of x equals f of g of h of x equals e to the cosecant of 2x. We have the following, and then we have the following. Find the derivative of sine of x using the limit definition of the derivative. Sine of x derivative equals this, which eventually equals that. Find the derivative of cosine of x using the limit definition of the derivative. We have this, and then we have that. Find the derivative of tangent of x. First we have this, and then we have that. Find the derivatives of cosecant of x, secant of x, and cotangent of x. First we have this, and then we have that. Find the quotient rule using chain rule. First we have this, and then we have that. Single variable calculus, differentiation, early transcendentals. In terms of pacing, this is 5 out of 18. What is the slope of the tangent line to a circle x squared plus y squared equals r squared? For explicit differentiation, we'd need to solve for y and then differentiate. We would get the following. But what if we couldn't solve for y? Implicit differentiation. For implicit differentiation, we treat y as a function of x, and then we differentiate both sides using various rules, which will result in a y prime term. We have the following. Sometimes we could solve for values through substitution rather than solving for a component in its generality. What is the second derivative for x squared plus y squared equals r squared? We have the following. Note that we can substitute y prime to find the second derivative. Let's find the derivatives of the inverse trigonometric functions. Here they are. Depending on how inverse cosecant and inverse secant are defined, it might be absolute value x in the denominator. For these, recall that f of f inverse of x equals x, and variations of the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. Find the derivatives of inverse sine, inverse cosine, and inverse tangent. Here they are. Find the derivatives of inverse cosecant and inverse secant. Here they are. Find the derivative of inverse cotangent. And we have the following. Early transcendentals. In this section, we'll find the derivatives of exponents and logarithms. Derivative of a to the x is a to the x ln a. Derivative of e to the x is e to the x. Derivative of log base a of x is 1 over x ln a. Derivative of ln x is 1 over x. We'll also differentiate constants and functions as bases and/or exponents. Derivative of a constant to a constant. Derivative of a function to a constant. Derivative of a constant to a function. Derivative of a function to a function. To find the derivative of f of x equals a to the x, use the limit definition of the derivative. F prime of x equals limit of h going to 0 of a to the x plus h minus a to the x all over h. It simplifies down to a to the x f prime of 0. Note that 1 equals a to the 0, and the last limit is the derivative of f of x equals a to the x at x equals 0. So, the derivative of f of x equals a to the x is proportional to a to the x itself, and that proportion is f prime of 0. We have the following. Approximately, if we let the base equal 2.72 and so on, then the proportion f prime of 0 is 1. And we have the following. We call this base number e, and so limit h opposed to 0 of e to the h minus 1 over h equals 1, and thus e to the x prime equals e to the x. Now, we can find the derivative of a to the x using chain rule. We have the following. Note the graphs of 2 to the x, e to the x, and 4 to the x, and their tangent lines at x equals 0. Here are the pictures. To find the derivative of f of x equals log base a of x, we use implicit differentiation. And we have the following. Now, we can find ln of x derivative equals log base e of x derivative equals 1 over x ln e equals 1 over x. Since ln is for x greater than 0, then its derivative 1 over x is for x greater than 0. However, ln absolute value x, which equals this, has the derivative 1 over x for x not equal 0. Note what happens when we differentiate ln absolute value x. We can express e as a limit using f of x equals ln x, f prime of x equals 1 over x, and f prime of 1 equals 1. We have the following. The last line used the substitution of x equals 1 over n, with n going to infinity as x going to 0 from the positive. Now, we can express e to the x greater than 0 as a limit. We have the following. The last line used the substitution m equals n over x becoming n equals xm, with n going to infinity as m goes to infinity. Logarithmic differentiation. To find the derivative of x to the x, we take logarithms of both sides. Here, to bring down exponents. Then we differentiate implicitly, and then we solve for y prime. We have the following. Logarithmic differentiation can not only bring down exponents, but can also simplify very complicated expressions. Consider f equals ab to the power c all over d, where each letter is a function. Normally, we would need quotient rule, product rule, chain rule, and so on. With logarithmic differentiation, after the following manipulation, we differentiate. Take logarithms of both sides. Logarithm rules. Nuance. If y is less than 0, then ln y is undefined, but we can take absolute values and then use the derivative of ln absolute value x along with chain rule. We can find the derivative of an inverse function using implicit differentiation. We have the following. Example. If we have f of x equals x cubed, what would be the derivative of the inverse function at 8? We have the following. Note, f of 2 equals 8, and so f inverse of 8 equals 2, as well as f prime of x equals 3x squared, and f prime at 2 equals 12. L'Hopital's rule. For an indeterminate form of type 0 over 0 or infinity over infinity, where these limits equal 0, or these limits equal positive or minus infinity, then we have the following. L'Hopital's rule helps us find limits when factoring, expanding, conjugates, and trigonometric identities don't work. We'll omit the other indeterminate forms, but they could be manipulated into these too. Let's find the limits of limit x approaches 1 of ln x over x minus 1 and limit x approaches infinity x squared over e to the x. We can only use L'Hopital's rule if we have indeterminate forms. We have the following. Note that we had to simplify in our algebraic manipulations. Growth of functions. In terms of growth, logarithms are slower than polynomials, than exponentials, than factorials, than tetration. In other words, in terms of growth, tetration is faster than factorials, than exponentials, than polynomials, than logarithms. We'll give the idea as to why on the following slide. For all the following ratios, we would have limit n goes to infinity equals infinity over infinity. And here is the following. Single variable calculus, differentiation, sketching, and extrema. In terms of pacing, this is 6 out of 18. An extremum, plural extrema, is a maximum or minimum. Maximums are larger than other values. Minimums are smaller than other values. Local or relative, extrema, are for an open interval containing that point, thus cannot be at an endpoint, basically near that point. Global, absolute extrema are for the whole domain or given domain, thus either in the interval or at endpoints. Extreme value theorem. A continuous function on a closed interval will have absolute extrema on that interval. Such extrema could occur multiple times. Fermat's theorem. If f has a local extrema at C, and if f prime of C exists, then f prime of C equals 0. A critical number of a function f is a number C in its domain of f such that either f prime of C equals 0 or f prime of C does not exist. Fermat's theorem. If f has a local extrema at C, then C is a critical number of f. Absolute extrema test. Since extrema are at either critical points or endpoints, we compare the values of the function there. The largest, or smallest, is the absolute maximum, or minimum. If on an infinite interval, then try to find local extrema that would eventually become global extrema. Here are some pictures. On the left, f prime goes from negative to 0 to positive, so the change of the first derivative is positive. That is, the derivative of the derivative, which is the second derivative, is positive. Here, f is increasing at an increasing rate and with tangents below. Concave up, a U shape, has f double prime greater than 0. Concave down, an N, has f double prime less than 0. An inflection point is where concavity changes. That is, second derivative changes sign. Note that concave up means the tangent lines yield under approximations. We'll note if f prime and f double prime are positive, negative, 0, or does not exist on these intervals. X less than 0, x equals 0, x greater than 0. Here is an example. For f equals x squared, the derivatives go from negative to 0 to positive when the intervals change from x less than 0 to x equals 0 to x greater than 0. Note that f double prime is always positive. For g equals absolute value x, the derivative goes from negative to not existing to positive when the intervals change from x less than 0 to x equals 0 to x greater than 0. The second derivative is omitted. Notes on how these upcoming slides are written. To keep the presentation concise, we'll limit counterexamples to the fewest and most basic ones that prove the point. Although other counterexamples exist, we'll omit them because these ones should be good enough. The logic of the statements is of utmost importance. Here are some examples. Can we tell if we have a max or min at a critical point, if prime equals 0 or does not exist? No. Both x squared and minus x squared have f prime of 0 equals 0, but we have a min and max. No. Both absolute value and negative absolute value have f prime of 0 does not exist, but we have a min and max. In fact, x cubed and minus x cubed have both f prime of 0 equals 0, but neither have a max or min. A sign change of the derivative at a critical point is decisive. Positive to negative is a max because we go up, then down. Negative to positive is a min because we go down, then up. Here are some examples. Can we tell if we have a max or min at f prime equals 0? No. Both x squared and minus x squared have f prime of 0 equals 0, but we have a min and max. If we have flatness from f prime equals 0, then the concavity from f double prime is decisive. Concave up from f double prime greater than 0 is a min because we're at the vertex of the U shape. Concave down from f double prime less than 0 is a max because we're at the vertex of the N shape. Note that f double prime equals 0 is not decisive since, for example, both x cubed and minus x cubed have f prime of 0 equals 0, and neither have a max or min. Here are some examples. Note that neither does f prime equals 0 nor f double prime equals 0 tell us anything if it's a max or min. Here's a picture. First derivative test. At a critical number, if f prime goes from positive to negative, then it's a local maximum, minus x squared. If f prime goes from negative to positive, then it's a local minimum, x squared. For maximums, we've increased all we can, and now we can only decrease. For minimums, we've decreased all we can, and now we can only increase. It is not simply f prime equals 0 or does not exist. Without checking a change of signs, we could have a maximum, a minimum, an inflection point, x cubed, or none. Consider a constant function. Use the first derivative test only when we can find if f prime is positive or negative to the left or right of a critical point. It works even regardless of f double prime. Here is a picture. Second derivative test. At f prime equals 0, if f double prime less than 0, then it's a local maximum, minus x squared. F double prime greater than 0, then it's a local minimum, x squared. When flatness occurs, we could have concave down for maximums and concave up for minimums. It is not simply f prime equals 0, because if f double prime equals 0, it could be a maximum, minus x to the power 4, a minimum, x to the power 4, an inflection point, x to the power 3, or none. Consider a constant function. The sign of f double prime must be strictly greater or less than 0. Use this test if we can't find positive negative nature of f prime to the left or right of a critical point, but have f prime equals 0 and a way of finding the positive negative nature of f double prime. To sketch, we first need to know what graphically happens when f prime, and f double prime is 0, positive, or negative. Negative, 0, positive. F value below x-axis, on x-axis, above x-axis. F prime slope, decreasing, flat or constant, increasing. F double prime concavity, N shape, 0, a U shape. To sketch f of x equals x cubed plus 3x squared, we first find the intervals where f prime, and f double prime are 0, positive, and negative. F of x, f prime of x, f double prime of x. Now we can interpret graphically what happens when f prime, and f double prime is 0, positive, or negative on those intervals. Here's a diagram. Now we start sketching in this order. Regarding f, we point out the zeros on the x-axis and then section out regions above and below the x-axis. Regarding f prime, we draw a curve that is decreasing or increasing, depending on the region, and then flats for the zeros. Regarding f double prime, we smooth out the curve so that there is a general N shape or U shape depending on the region. Regarding f, we point out the zeros on the x-axis and then section out regions above and below the x-axis. Regarding f prime, we draw a curve that is decreasing or increasing depending on the region and then flat for the zeros. Regarding f double prime, we smooth out the curve so that there is a general N shape or U shape depending on the region. Here's a picture. We can get the general shape of the curve, but the only values that we truly know are x-axis intercepts, where f of x equals 0, explicitly minus 3, 0, and 0, 0. Note that f seems to have a local maximum at x equals minus 2, an inflection point at x equals minus 1, a local minimum at x equals 0. We can prove this by returning to the chart with the intervals where f prime, and f double prime are 0, positive, and negative. Here are the values. First derivative test. Regarding f prime, note the following positive negative changes of sign. At x equals minus 2, we go positive to negative, This is a maximum since we go up then down. At x equals 0, we go negative to positive. This is a minimum since we go down then up. Second derivative test. When we're flat, that is f prime equals 0, note the positive negative sign of f double prime. At x equals minus 2, f double prime less than 0. This is a maximum since we're concave down and flat. At x equals 2, f double prime is greater than 0. This is a minimum since we're concave up and flat. Inflection points. Where does f double prime change sign? At x equals minus 1. Here is a picture. Evaluating f at these values of x, we get these important points. X-intercepts of negative 3, 0, and 0, 0, and y-intercept of 0, 0. Relative maximum of minus 2, 4, and relative minimum of 0, 0. Inflection point at minus 1, 2. Here's the picture. Now, let's restrict our domain to negative 3.1, 1.1. Based upon the candidate test, what would be the absolute maximum and minimum? For the candidate test, we evaluate f at the critical points, f prime equals 0 or does not exist, and at the endpoints. On the interval, negative 3.1 to 1.1, note the following. The absolute minimum is this and occurs at x equals minus 3.1. The absolute maximum is this and occurs at x equals 1.1. Mean value theorem for derivatives. Let f be a function that satisfies the following hypotheses. F is continuous on the closed interval ab. F is differentiable on the open interval ab. Then there is a number c in ab such that this tangent line slope equals secant line slope. Rolle's theorem. In addition to the mean value theorem, if f of a equals f of b, then the secant line slope is 0, and so there is a horizontal tangent. Consider f of x equals x squared. On 0, 2, the mean value theorem shows that f prime of a equals 2 for some a in 0, 2, since we have this. On minus 2, 2, Rolle's theorem shows that f prime of b equals 0 for b in negative 2, 2, since we have this. We have three existence theorems that prove a point exists if the requirements are fulfilled, but we don't know that point explicitly. The intermediate value theorem regarding values, if there is continuity. The extreme value theorem regarding absolute extrema, if there is continuity and a closed interval. The mean value theorem regarding derivatives, if there's differentiability. A rectangle has a perimeter of 20 units. What are the side lengths of the rectangle that has the largest area? We have two equations and two unknowns. Area, perimeter. We want to maximize the area function, but we can't do it directly since it is in terms of two variables. So we have to solve our perimeter function for one variable and then substitute it into the area function. That way, we would have the area function in terms of one variable. Let's solve for b. Mathematically, it doesn't matter which variable, but it might matter which one when solving by hand. If we solve for b, we get this, and we have to note its domain is this. Although we get degenerate rectangles, that is lines, at the endpoints, we still need the endpoints. And so the area function and its derivatives become this. Note that the critical points, when a prime of h equals 0 does not exist, is when h equals 5. To find the absolute extrema, we evaluate a of h equals 10h minus h squared at its possible candidates, that is, the critical points and endpoints. A of 0 equals 0, a of 5 equals 25, a of 10 equals 10. The largest of the values is the absolute maximum, and smallest for minimum. For us, it means that a rectangle with a perimeter of 20 has a maximum area of 25 with side lengths of 5. Now, in some cases, we could analyze the first derivatives to find relative extrema that could eventually become absolute extrema. Consider finding the maximum area by applying the first derivative test. We have the following. Note that the relative maximum at h equals 5 becomes an absolute maximum. A prime of h greater than 0 for h less than 5, and a prime of h less than 0 for h greater than 5. By similar logic, an absolute minimum would have f prime changing from negative to positive at its critical point. A circle's area is increasing at a rate of 18 pi square units per second. When the area of the circle is 9 pi square units, how fast is its radius increasing? In a static situation, the area relies only on the radius. However, in a dynamic situation, the area eventually relies on the time. Note that, in differentiating our dynamic situation, we need chain rule. Static, dynamic, differentiate with respect to t. Here, we used chain rule. In other questions, we might need quotient rule, product rule, etc. Also, in other questions, there might be more variables, but only certain ones might change with respect to time. Now, after differentiation, we can start replacing values that we know or could solve for. We have the following. Note, although we solved r prime of t equals 3, we don't actually know what t is. Here are other examples of how differentiation is done in related rate questions. Cones, similar triangles. Single variable calculus, integration, intuition, and calculations. In terms of pacing, this is 7 out of 18. We can approximate the area under f of x equals x with x between 1 and 3, and above the x-axis with rectangles of heights at sample points xi star on intervals. Reds underestimate the area, blues overestimate the area. But these approximations get better and closer with more and thinner rectangles. In other words, we get the area with a limit of Riemann sums. Riemann sums give the approximate area of f of x equals x from a equals 1 to b equals 3. For us, we'll use two rectangles, and so delta x equals b minus a over n equals 3 minus 1 over 2 equals 1. Note that the left or right Riemann sums gives the values on the left or right of the interval. Note that if f is increasing, then left is less than actual area less than right. Similarly, if f is decreasing, then right is less than actual area is less than left. The limit of right Riemann sums will give the area of f of x equals x from 1 to 3. Here is the formula. Here are the specifics. Although we won't do it, the left Riemann sums, Ln, needs k minus 1 rather than k. Either way, the area comes from the limits. A equals limit as n approaches infinity Rn equals limit as n goes to infinity Ln. Note that B will depend on the largest sample. In this case, since k goes to n, we have a plus k delta x equals a plus n delta x equals b. These calculations show that the limit of the series becomes 4. Although we won't do them, there are midpoint sums and trapezoidal sums. If f is concave up, then midpoint is less than actual area less than trapezoid. If f is concave down, then trapezoid is less than area less than midpoint. Here is the definite integral of f from a to b. If the limit exists, then f is integrable on a to b. The symbol is called an integral sign. The f of x is called the integrand. The a is the lower limit of integration, and b is the upper limit. The symbol dx indicates that we are integrating with respect to x. The procedure of calculating an integral is called integration. Our original example now becomes integral from 1 to 3 x dx equals 4. The definite integral is a number. It doesn't depend on the variable of integration. When going left to right, areas above the x-axis are considered positive, areas below the x-axis are considered negative. The definite integral is the net area of the function above the x-axis. Constant, sum and difference, constant multiple, additivity, zero width, reversibility. Direction of the integral, to the right and to the left. Inequality, max and min, average, mean value. One can think of the average value as the height of the rectangle that has the same area and base as the function. Even function, odd function. The fundamental theorem of calculus 1. If f is continuous on closed interval ab, then with a less than or equal to x less than or equal to b, g of x equals integral from a to x f of t dt, g prime of x equals f of x, is continuous on closed interval ab and differentiable on open interval ab, and g prime of x equals f of x. The derivative of the accumulation, area so far, function, g of x is f of x. The following slide just gives the idea. It is not formal at all. Starting with the function f, the accumulation function g of x equals integral from a to x f of t dt gives the area under the graph from a to x. Starting at a, we find the area up to x, and then up to x plus h. The difference in areas as h approaches 0 is approximately a rectangle with base h and height f of x. As h approaches 0 is approximately rectangular area, divide by h, and limit. What is the derivative of g of x equals integral from 0 to x e to the t squared dt? Here, f of t equals e to the t squared. Recall that g prime of x equals f of x, so g prime of x equals e to the x squared. What is the derivative of g of x equals integral 0 to x squared e to the t squared dt? Like before, f of t equals e to the t squared. Unlike before, here we have g of u where u equals x squared. To differentiate this composite function, we'd need chain rule. G of x equals g of u of x equals integral 0 to u e to the t squared dt. G prime of x equals g prime of u of x, u prime of x, equals f of u of x, u prime of x, equals e to the u squared times 2x equals 2x e to the x to the 4. What is the derivative of g of x equals integral x to x squared e to the t squared dt? Unlike before, we have x in both limits of integration and not just the upper. We need to split the integral and use reversibility. What is the derivative of g of x equals integral x squared to x cubed e to the t squared dt? Like before, we have to split the integral and use reversibility. The fundamental theorem of calculus 2. If f is continuous on closed interval ab, then integral from a to b f of x dx equals big F of b minus big F of a, where big F is any antiderivative of little f, that is, where big F prime equals f. The most general antiderivative of little f is big F plus c, constant, since a constant differentiated becomes 0. Note that the integral of a rate of change is the net change. Now we can relate the accumulation function and the antiderivative. G of x equals integral from a to x f of t dt. G prime of x equals f of x. G of x plus c equals big F of x. From this, on the next slide, we'll see that this due to changes in the accumulation function. Here are the details. Note that plus c's cancel out in definite integrals. Big F of b minus big F of a equals g of b plus c minus g of a plus c equals g of b minus g of a, which equals this from definition of g of x, equals integral a to b f of t dt. Fundamental theorem of calculus 1 and 2. If f is continuous on closed interval ab, then we have g of x equals integral a to x f of t dt, g prime of x equals f of x, and where big F prime equals f, then integral from a to b f of x dx equals big F of b minus big F of a. Basically, integration and differentiation are inverse processes. Compiling all the terms, using f of x equals x as our example, the antiderivative of little f is big F, where big F prime equals little f. Big F of x equals x squared over 2, as well as x squared over 2 plus 1, x squared over 2 minus 1, and so on. The indefinite integral of little f is a set of functions whose derivative is little f. Integral x dx equals x squared over 2 plus c, where we have antiderivatives for each value c. The accumulation function gives the area of little f from a fixed a to a variable x. G of x equals integral a to x f of t dt. The definite integral is a number that represents the net area. Integral 1 to 3 x dx equals 4. For definite integrals, we find the simplest antiderivative with c equals 0 and take out any constant multiple. Evaluate at the upper limit of integration minus the lower limit of integration. Calculation nuances. For f of x equals 1 over x, the most general antiderivative is not ln x plus c, nor ln absolute value x plus c. Rather, it is big F of x equals this, to account for the different branches of 1 over x. For us, we'll use ln absolute value x plus c, and then see if the absolute value is necessary. We'll revisit this nuance when we do differential equations. If there is a jump discontinuity, we could still find the integral by splitting up the interval. A point discontinuity does not affect the overall integral. Note that integral dx equals integral 1 dx. For applications, integral from start to end of the rate dx equals quantity from start to end equals quantity at the end minus quantity at the start. Becomes this. In words, we add our starting amount with the accumulation of small changes, which equals the overall net change, so that we get the ending amount. For these examples, we should ask two questions. Is the function continuous on the interval? What sign do we expect? A positive, negative, or 0? A template for the calculations could be the following. Integral from x equals 1 to x equals 4 of negative x plus 3 dx. We get 3 over 2. Integral from x equals 1 to x equals 4 of negative x plus 2 dx, and we get minus 3 over 2. Integral from x equals 1 to x equals 3 of minus x plus 2 dx, we should get 0. Integral from x equals 1 to x equals 2, 1 over x dx, we should get ln 2. Note that the antiderivative of 1 over x is ln absolute value x, and it becomes ln x when the x value is positive. Integral x equals minus 2 to x equals minus 1, 1 over x dx, we get minus ln 2. Note that the antiderivative of 1 over x is ln absolute value x, and it remains ln absolute value x when the x value is negative. Integral x equals minus 1 to x equals 2, 1 over x squared dx. It is not continuous on the interval, and we expect positive. We get minus 3 over 2. Since the integrand is not continuous on the interval, none of the computations are valid. Integral x equals 0 to x equals 1, 2x squared dx should get 2 over 3. Integral of x equals 1 to x equals 2 of x plus 1 squared all over x squared dx. It's continuous on the interval, and so we have the following, and we get 2 ln 2 plus 3 over 2. Find the indefinite integral of this. We get cosecant theta plus secant theta plus c. If we had information like f of pi over 4 equals 2 root 2, then we could solve for c equals 0. If f double prime of x equals 6x, and f prime of 0 equals 2, and f of 0 equals 1, then what is f of x? We have the following. Now we can solve for c. We have the following. Now we can solve for d. F of x equals x cubed plus 2x plus 1. If f equals t cubed x to the power 4, to find this, we treat only box as a variable and everything else as a constant. And we have the following. After integrating, we can differentiate with respect to the variable and get our original function. To find this, we treat only box as a variable and everything else as a constant. And we get the following. Single variable calculus, integration, substitution. In terms of pacing, this is 8 out of 18. Let's find integral x equals 1 to x equals 2 of 2x plus 1 squared dx. We get 49 over 3. But can we do it without expanding the integrand? If our integral was just something squared, then u equals 2x plus 1. And we get the following. Our integrand is in terms of u, and so we need du rather than dx. And we get the following. Our limits of integration needs to be in terms of u rather than x. And we get the following. Integral of x equals 1 to x equals 2, 2x plus 1 squared dx equals integral u equals 3 to u equals 5, u squared du over 2. Having converted our integral in terms of x's to one of u's, we calculate. For indefinite integrals, we substitute u, so our answer is with respect to x. Integration by substitution. Here are the details. Integration by substitution is the opposite of differentiation by chain rule. We need u to be the inner function gx, and we also need a constant multiple of its derivative, g prime of x. Integral 1 to 2 x squared plus 1 squared dx. We get 39 over 2. Integral 1 to e ln x over x dx. We get half. Integral tan x dx ln absolute value secant of x plus c. Integral x square root 2x plus 1 dx. Not only do we have u substitution, but we also have manipulation of u. We get 1/10 2x plus 1 to the power of 5 over 2 minus 1/6 2x plus 1 to the power of 3 over 2 plus c. Integral x to the power of 5 square root x squared plus 1 dx. Not only do we have u substitution, but we also have manipulation of u. We get 1/7 x squared plus 1 to the power of 7 over 2 minus 2/5 x squared plus 1 to the power of 5 over 2 plus 1/3 x squared plus 1 to the power of 3 over 2 plus c. Integral of 1 over x squared plus 2x plus 2 dx, which equals integral of 1 over x squared plus 1 squared plus 1 dx. We get arctan x plus 1 plus c. Single variable calculus, integration, fundamental theorem of calculus. In terms of pacing, this is 9 out of 18. Each box above is 1 unit squared. Based upon the graph of f of x above, what are the intervals where g of x, which equals integral from 0 to x f of t dt, is positive or negative, increasing or decreasing, concave up or concave down? Do not use graph first. Use calculus first. G of x equals integral from 0 to x f of t dt. G prime of x equals f of x. G double prime of x equals f prime of x. When the g is positive or negative, increasing or decreasing, concave up or concave down. When is g of x positive? For g, x greater than 0 equals integral from 0 to x f of t dt, the area above is more than the area below. For g, x less than 0, equals minus integral of x to 0 f of t dt, the area below is more than the area above. When is g of x increasing? When is g prime positive? When is f of x positive? When is the graph of f above the x-axis? When is g of x concave up? When is g double prime of x positive? When is f prime of x positive? When is the graph of f increasing? When is g of x positive? For x greater than 0, when the area above is more than the area below, from 0 to 1. For x less than 0, when the area below is more than the area above, from -3 to -2. When is g of x negative? For x greater than 0, the area above is less than the area below, from 1 to 3/2. For x less than 0, the area below is less than the area above, -2 to 0. When is g of x increasing? The graph of f is above the x-axis, -1 to half. When is g of x decreasing? The graph of f is below the x-axis, -3 to -1, and half to 3/2. When is g of x concave up? The graph of f is increasing, -3 to 0. When is g of x concave down? The graph of f is decreasing, 0 to 3/2. Note the inflection point at x equals 0 since the concavity changes. For f graphs, since g double prime equals f prime, we'll have inflection points whenever f changes from increasing to decreasing or decreasing to increasing. So the number of extrema for f is the number of inflection points for g. What are the extrema for g of x? For the local extrema, recall the first derivative test as well as the second derivative test. For global extrema, recall the candidate test. Using the first derivative test, find where the derivative changes sign. Local minimum, when g prime of x goes from negative to positive, x equals -1. Local max, when g prime of x goes from positive to negative, x equals half. Using the second derivative test, find the concavity when the derivative equals 0. Local min, g prime of x equals 0, and g double prime of x greater than 0, x equals -1. Local max, g prime of x equals 0, and g double prime of x less than 0, x equals half. To find the global extrema, consider the candidate test, where we calculate g of x at the critical points, g prime of x equals 0 or does not exist, and the endpoints. We get the following. Global minimum of -3/4 is at x equals 3/2, and the global maximum of 3/2 is at x equals -3. Each number stated above is area enclosed, and each notch on the x-axis is 2 units. Based upon the graph of f prime of x above, and noting that f of 4 equals 0, what are the intervals where f of x is positive or negative, increasing or decreasing, concave up or concave down? Do not use graph first. Use calculus first. Integral from 4 to x f prime of t dt equals f of x minus f of 4, which becomes f of x equals f of 4 plus integral 4 to x f prime of t dt. F prime of x is given. F double prime of x equals f prime of x derivative. When is f of x positive or negative, increasing or decreasing, concave up or concave down? When is f of x positive? For f of x greater than 4, which equals f of 4, which equals 0, plus integral 4 to x f prime of t dt, the area above is more than below. For f of x less than 4, which equals f of 4, which equals 0, minus integral from x to 4 f prime of t dt, the area below is more than above. When is f of x increasing? When f prime of x is positive. When is the graph of f prime above the x-axis? When is f of x concave up? When is f double prime of x positive? When is f prime of x increasing? When is the graph of f prime increasing? When is f of x positive? For x greater than 0, when the area above is more than the area below. Nowhere. For x less than 4, when the area below is more than the area above. Nowhere. When is f of x negative? For x greater than 4, when the area below is more than the area above. From 4 to 8. For x less than 4, when the area above is more than the area below. From 0 to 4. When is f of x increasing? When the graph of f prime is above the x-axis. 2 to 4 and 6 to 8. When is f of x decreasing? When the graph of f prime is below the x-axis. 0 to 2 and 4 to 6. When is f of x concave up? When the graph of f prime is increasing. 1 to 3 and 5 to 7. When is f of x concave down? When the graph of f prime is decreasing. 0 to 1, 3 to 5, and 7 to 8. Note the inflection points at x equals 1, 3, 5, and 7 since the concavity changes. For f prime graphs, since f double prime equals f prime prime, we'll have inflection points whenever f prime changes from increasing to decreasing or decreasing to increasing. So the number of extrema for f prime is the number of inflection points for f. What are the extrema for f of x? For local extrema, recall the first derivative test as well as the second derivative test. For the global extrema, recall the candidate test. Using the first derivative test, find where the derivative changes sign. Local minimum. When f prime of x goes from negative to positive, x equals 2 and x equals 6. Local max. when f prime of x goes from positive to negative, x equals 4. Using the second derivative test, find the concavity when the derivative is 0. Local min, f prime of x equals 0, and f double prime of x greater than 0, x equals 2, and x equals 6. Local max, f prime of x equals 0, and f double prime of x less than 0, x equals 4. To find a global extrema, consider the candidate test, where we calculate f of x at the critical points, f prime of x equals 0 does not exist, and the endpoints. We have the following. Global minimum of minus 3 at x equals 2, and the global maximum of 0 at x equals 4. Single variable calculus, applications, movement. In terms of pacing, this is 10 out of 18. A particle has v of t equals 3t squared minus 12t plus 9, and p of 0 equals 0. What are the zeros of position, velocity, and acceleration? PVA. Here are the integral derivative relationships, and be careful about plus c. We have the following. To find the zeros of position p of t, note that integral v of t dt equals p of t plus c. Since p of 0 equals 0, then c equals 0. So p of t equals 0 when t equals 0 or 3. To find the zeros of velocity, v of t, we factor our given expression. So v of t equals 0 when t equals 1 or 3. To find the zeros of acceleration, a of t, note that v of t prime equals a of t. So a of t equals 0 when t equals 2. Initial means t equals 0, so initial velocity is 9, and at rest means v of t equals 0. Velocity greater than 0, velocity less than 0. Acceleration greater than 0, time 1, time 2. Speed. Acceleration less than 0, time 1, time 2. Speed. Consider positive and negative pairings of velocity and acceleration for time 1 to time 2. Speed is the length of velocity, that is, s equals absolute value v. If the length of the velocity vector increases, then the speed increases. Speed increases when both velocity and acceleration have the same sign. We're moving right, then faster right, or moving left, then faster left. E of t, v of t, a of t. On 0 to 1 and 3 to 4, the change of position, which is velocity, is positive. On 0 to 2, the change of velocity, which is acceleration, is negative. When t equals 1, the change of position goes from getting more positive to getting more negative. So velocity goes from positive to negative. When t equals 2, the change of velocity goes from getting more negative to getting more positive, so acceleration goes from negative to positive. Speed is increasing for 1 to 2 and 3 to 4 due to same sign of velocity and acceleration. If we integrate velocity, we would get displacement, change of position. We have the following. If we integrate acceleration, we would get the change of velocity. Here's the following. We can rearrange these above integrals to solve for p or v at a certain time. If we integrate speed, we would get total distance traveled. What is the total distance traveled between time 1 equals 0 and time 2 equals 4? If we split the integral into sections where the integrand is strictly non-positive or non-negative, then we can move out the absolute value sign. In general, however, this does not equal that. And we have the following. To transform each of these three integrals to the positions, consider this. V, P. And we have the following. In splitting the integral into sections, we found the change of the positions while moving in one direction. This way, there is no overlap. Generally, velocity is positive when moving right, forward, or up. What is the average position, Pf of t, between t1 equals 0 and t2 equals 4? We have this, which equals 2. What is the average velocity, Vv, of t between t1 equals 0 and t2 equals 4? Average velocity, which is average rate of change of position, which is slope of secant line of position, and we get 1. What is the average acceleration, a av, of t between t1 equals 0 and t2 equals 4? Average acceleration, average rate of change of velocity, slope of secant line of velocity, and we get 0. What is the average speed, Sav, of t between t1 equals 0 and t2 equals 4? If we split the integral into sections where the integrand is strictly non-positive or non-negative, then we can move out the absolute value sign. In general, however, this does not equal that. And we get 3. Single variable calculus, applications, area and volume. In terms of pacing, this is 11 out of 18. We think of area as adding up infinitely many infinitesimally thin rectangles. Here are some pictures. Integration with respect to x works well for regions with two different upper and lower functions. Similarly, integration with respect to y works well for regions with two different left and right functions. Let's find the area between y equals 2x and y equals x squared with an integral using dx. Our limits of integration are the x-coordinates of the intersections. 2x equals x squared has intersections 0, 0 and 2, 4, and so we use 0 and 2. Our integrand is the length with respect to x. 2x, which is upper, minus x squared, which is lower, since the following. Now we can compute the integral. And we get 4 over 3. Let's find the area between y equals 2x and y equals x squared with an integral using dy. Our limits of integration are the y-coordinates of the intersections, 0, 4. Our integrand is the length with respect to y, and note how we had to solve. Square root y, which is right, minus y over 2, which is left, since the following. Now we can compute the integral. And we get 4 over 3. If there are two curves that alternate between larger and smaller function, then we need to figure out which one is which on each interval. We could use absolute values, but we'd have to split the integral if doing calculations by hand. Find the area between x cubed and x. The intersections are x equals -1, 0, 1. Note that x cubed greater than or equal to x on -1 to 0, and x greater than or equal to x cubed on 0 to 1. We have the following, which equals half. We think of volume, loaf, as adding up infinitely many infinitesimally thin cross-sectional areas A, slices. For rotations, the cross-sections are circles. If they're solid, they're called disks, and if they have holes, they're called washers. Here are some pictures. The base of the solid is the region enclosed by y equals 2x and y equals x squared, and cross-sections perpendicular to the x-axis are squares, then y-axis. The areas of square cross-sections are A equals length squared. With dx, we get 16 over 15. With dy, we get 8 over 15. The region enclosed by y equals 2x and y equals x squared is rotated around the x-axis, then y-axis. The area of washer cross-sections are A equals pi radius big squared minus pi radius small squared. With dx, we get 64 pi over 15. With dy, we get 8 pi over 3. Note, if we rotate it around y equals -1, then A equals this. Single variable calculus, applications, differential equations. In terms of pacing, this is 12 out of 18. A differential equation is an equation with an unknown function and its derivatives. For example, dy dx equals ky is exponential growth if k is greater than 0, and exponential to k if k is less than 0. A solution to a differential equation is a function and its derivatives that satisfy it. For example, for above, y equals c e to the x. To draw a slope field for the differential equation dy dx equals y, we draw short line segments with slope y at point xy. To draw a solution curve, we trace the path made by a particular function y that goes to a particular point called an initial condition. The paths are where have we been and where will we go. The blue is the solution curve going through 0, 2, red 4, 0, -3. Let's use Euler's method with 3 steps to approximate values of the solution curve. For the blue solution curve, we'll start at 0, 2 and to approximate y of 1.5. For the red solution curve, we'll start at 0, -3 to approximate y of -1.5. To do Euler's method, we start at the point given by the initial condition and go in the direction of the slope field for a given step size. After that step size is completed, we go in the direction of the slope field at that new point for the given step size. In this way, we have step-by-step tangent line approximations. And here's a picture. Use Euler's to approximate y of 1.5 for dy dx equals y using 3 steps starting at 0, 2. Here are some pictures. We have 3 steps to reach y of 1.5, so x equals 1.5. And so dx equals 0.5. Our differential equation dy dx equals y gives the slope at 0, 2 as 2, and so dy equals 1. So our new point, yx n plus 1, equals x plus dx, y plus dy, is 0.53. Repeating this twice, we get y of 1.5 approximately 6.75. Note y of 1.5 equals 8.963 and so on. Use Euler's to approximate y of 1.5 for dy dx equals y using 3 steps starting at 0, 2. Here is a table. Let's redo the question with this table way of Euler's method. With 0 steps, n equals 0, we're at 0, 2, the slope is 2, and dy equals 1. We take 1 step, n equals 1, to reach 0.53. Repeat. Repeating this twice, we get y of 1.5 approximately 6.75. Note y of 1.5 equals 8.963 and so on. Use Euler's to approximate y of negative 1.5 for dy dx equals y using 3 steps starting at 0, negative 3. Here is the table. We have 3 steps to reach y of negative 1.5, so x equals negative 1.5, and so dx equals negative 0.5. With 0 steps, n equals 0, we're at 0, negative 3. The slope is negative 3, and dy equals 1.5. We take 1 step, n equals 1, to reach negative 0.5, negative 1.5. Repeat. Repeating this twice, we get y of negative 1.5 approximately negative 0.375. Note y of negative 1.5 equals negative 0.669 and so on. Before separation of variables, we must note this nuance regarding integral 1 over x dx. First, consider the domains of ln x and 1 over x. Ln x with x greater than 0, 1 over x with x not equal to 0. Derivatives f prime of x have, at most, the same domain as their functions f of x. F of x equals ln x with x greater than 0. F prime of x equals 1 over x with x greater than 0. But what function could have the derivative f prime of x equals 1 over x with x not equal to 0? Since x not equal to 0 means x greater than 0 and x less than 0, then f prime of x equals 1 over x with x not equal to 0 becomes f prime of x equals 1 over x for x greater than 0, 1 over negative x times negative 1, which is 1 over x for x less than 0. Recall the piecewise definition of absolute value. X for x greater than 0 or equal to 0, negative x for x less than 0. Maybe the function whose derivative is 1 over x is logarithm with the absolute value. Ln curved bracket absolute value x equals ln absolute value x equals ln of x, x greater than 0, ln negative x, x less than 0. Indeed, the derivative of ln absolute value x is 1 over x since ln absolute value x equals ln x, x greater than 0, ln negative x, x less than 0. ln absolute value x prime equals 1 over x for x greater than 0. 1 over negative x times negative 1 equals 1 over x for x less than 0. But recall that a constant differentiated becomes 0. Since the right and left branches of ln absolute value x are discontinuous, the right and left c's could be different. Ln absolute value x plus c equals ln x plus c1 for x greater than 0, ln negative x plus c2, x less than 0. For simplicity, we use ln absolute value x plus c even though the c's are different. Finally, since we've seen how ln absolute value x plus c prime equals 1 over x, we have integral of 1 over x dx equaling integral 1 over x dx, x greater than 0, integral 1 over negative x times negative 1 dx for x less than 0, equals ln absolute value x plus c, which is ln x plus c1 for x greater than 0, ln negative x plus c2 for x less than 0. In practice, if given an indefinite integral, then we'll use the absolute value logarithm, ln absolute value x, since we don't know if we're using the right or left branch. If we know which branch, then we can simplify based upon if x greater than 0 or if x less than 0. Let's solve the differential equation dy dx equals y with initial condition 0, 2. Separation of variables and integrate. Combine constants of integration on right side. Ln absolute valued y becomes ln of y due to the positive input. Solving constant of integration with point 0, 2. Substituting constant of integration. Solving for y and simplifying. And we get y equals 2e to the x. Let's solve the differential equation dy dx equals y with initial condition 0, negative 3. Separation of variables and integrate. Combine constants of integration on right side. Ln absolute valued y becomes ln negative y due to the negative input. Solving constant of integration with point 0, negative 3. Substituting constant of integration. Solving for y and simplifying. And we get y equals negative 3e to the x. Let's solve the differential equation dy dx equals ky with initial condition 0, y0. Separation of variables and integrate. Combine constants of integration on right side. Solve for absolute value y and simplifying. Solving for y. Using the initial condition 0, y0, we find that plus minus e to the c is y0. Solution to dy dx equals ky with point 0, y0. Note, y0 could also equal 0 since that solution was lost when we divided by y. dy dx equals ky is exponential growth, the light blue. dy dx equals ky 1 minus y over m, or cy m minus y, with k equaling cm, is logistic growth for blue, k greater than 0, or logistic decay red for k less than 0. Exponential growth, light blue, for population will grow without bound. But this is unrealistic. Logistic growth, blue, is when the population growth is limited to a maximum population, m, called the carrying capacity. Limit as time goes to infinity of y equals m. Using implicit differentiation, we'll find that the population grows fastest when it's half the carrying capacity, which is also the curve's inflection point. Note that y prime equals 0, no growth, is when y equals 0 or y equals m. Single variable calculus, applications, parametric and polar. In terms of pacing, this is 13 out of 18. Coordinate system, slope, area, length. Rectangular, parametric, polar. Rectangular example with line. Rectangular functions use the x inputs that varies from a to b to get the y outputs using f of x equals y. Parametric example with asteroid. Parametric equations use the input parameter t that varies from a to b to get x and y outputs using f of t equals x and g of t equals y. A parametric curve has direction since it goes from its initial point to its terminal point. X equals cosine t cubed and y equals sine t cubed with t greater than or equal to 0, less than or equal to 2 pi. Polar example with cardioid. The polar coordinates of a point P is r of theta, theta, where r is the distance between the origin O and P, and theta is the counterclockwise angle between the polar axis, which lies on the positive x-axis, and the line OP. Negative radius means going in the direction of that angle, but backwards. Note that r squared equals x squared plus y squared, and tangent theta equals y over x. R of theta equals 1 plus sine of theta, with theta greater than or equal to 0, less than or equal to 2 pi. Slope, parametric. To find the slope for parametric, we start with the slope for rectangular, dy dx, and use chain rule. Note that x equals f of t and y equals g of t. To find the second derivative, replace y with dy dx in the formula. Let's find the slope of the asteroid, x equals cosine t cubed and y equals sine t cubed. Dy dx ultimately equals minus tangent of t. Slope, polar. To find the slope for polar, we adapt the parametric slope by replacing t with theta. Note that x of theta equals r of theta cosine theta, and y of theta equals r of theta sine of theta need product rule. Dy dx equals the following. Let's find the slope of the cardioid, r of theta equals 1 plus sine of theta. In practice questions, we will probably evaluate this for a certain angle. Dy dx equals the following. Area, polar. To remember the area formula for polar, consider a circle's area in relation to how much angle we've traveled. Area, angle. Pi r squared, 2 pi. I squared over 2, 1, half I squared theta, theta. Eventually, we'll get integral from a to b half I squared d theta. Be careful if finding the area between two polar functions, because it's not simply subtracting the larger function f and the smaller function g. Area inside larger function f minus area outside smaller function g. And we get the following. For questions, find the angles for the intersection points and use those as the limits of integration. In practice questions, there can be multiple equivalent setups of the integrals due to symmetry. Let's find the area enclosed by the cardioid r of theta equals 1 plus sine of theta, with theta greater than or equal to 0, less than or equal to 2 pi. We have the following. In practice questions, we might use identities like the following. Here are the calculations. By the way, calculations could have been simpler if we had noted that the integrals for the second and third addends are 0 since they're over full periods. Length, rectangular and parametric. The formulas for length are based upon the Pythagorean theorem. The parametric formula comes from substituting dy dx equals this and dx equaling this. Let's find the perimeter of the asteroid x equals cosine t cubed and y equals sine t cubed, with t greater than or equal to 0, less than or equal to 2 pi. Start with 4 times the length in the first quadrant. And we get the following. Continuing. With simplification, since sine of t and cosine t are positive for t greater than or equal to 0, less than or equal to pi over 2, we get the following. Parametric movement. The parametric first and second derivatives can be applied to position, velocity, acceleration questions. And we have the following. Note that speed is the absolute value of velocity, that is, the length of the velocity vector. And we have the following. Single variable calculus, integration, parts, fractions, improper. In terms of pacing, this is 14 out of 18. Integration by parts. Integral u dv equals uv minus integral v du. Integration by parts is for integrands that have different kinds of functions. The choice for u is based upon liate. Logarithm, where du could simplify the integrand. Inverse trigonometry. Algebraic, polynomial. Trigonometric, exponential, where dv would be easy to integrate. We use product rule to find the integration by parts formula. There is this formula for definite integrals, though it's easier just to find the difference between the antiderivatives. The upcoming slides are for the following easy integrals. Here. We won't be doing 1. Integrals like integral x squared e to the x dx that have repeated integration by parts, nor 2. Integrals like e to the x sine x dx that have solving for integrals. integral x sine x dx, integral x ln x dx, integral x e to the x dx, integral ln of x dx equals x ln x minus x plus c. Integral inverse tangent of x dx Before we do partial fraction decomposition, just because we have a rational function doesn't mean we use partial fractions. Consider simple, simple division, simplification, long division, and substitution, where we have the following. For the long division, note that this. Another example of division is this. Partial fractions. Consider this integral. First factor the denominator. We split up the fraction, but we don't know the numerators. To find the values of a and b, consider multiplying by the denominator. If x equals 0, then b's coefficient is 0, and we'll find a. With x equals minus 1, we'll find b. Having separated the fractions and found the numerators, we integrate. Generally, for some questions, logarithmic identities are used a lot. Improper integrals. Let's consider integrals where the limits or integrands go to infinity. For these improper integrals, we cannot substitute infinity in calculations. We have to transform the integral into a limit and take that limit to infinity. If the limit exists, then the integral is convergent. Otherwise, it's divergent. Here are the integrals, and we should get the following. For these improper integrals, we cannot substitute values that will result in undefined in calculations. We have to transform the integral into a limit and take that limit to that value based upon how we approach it. If the limit exists, then the integral is convergent. Otherwise, it's divergent. Here are the integrals, and we should get the following. If we generalize the exponents, we would get the following. This and that. Here are functions and improper integrals. Note that if it's bigger than something that diverges, then it diverges. And if it's smaller than something that converges, then it converges. The idea doesn't work in reverse. That is, if it's bigger than something that converges, it may or may not converge. And if it's smaller than something that diverges, then it may or may not diverge. We need non-negative functions since that lower bound squeezes the integral. For improper integrals with integration by substitution, integral 1 to infinity x squared e to the negative x to the power 3 dx. We get the following. We'll call integration by substitution. And here are the calculations. We call a limit x to 0 from the positive side ln x equals minus infinity, and so it has a vertical asymptote of x equals 0. For improper integrals with integration by parts, integral 0 to 1 ln x dx. We get the following. We call integration by parts. We get the following. Need L'Hopital's rule to do the first limit, and we get the following. Or improper integrals with integration by partial fractions. Integral 1 to infinity 1 over x squared plus x dx. We get the following. We call integration by partial fractions. And we get these calculations. Nuance about divergence. Regarding convergent and divergent integrals, convergent and convergent is convergent, convergent and divergent is divergent, divergent and divergent is inconclusive since it could either converge or diverge. The first integral diverges, but the second integral converges. Divergence doesn't mean positive, negative infinity. For example, note the oscillation. And we get the following. Nuance about double infinities. If both this and that integral converges, then we can define this. Generally, this is not the same as that. On the next slide, we'll consider the example of f of x equals sine of x. On the left side, I note that cosine x equals cosine minus x since cosine x is even. And we get the following. On the right side, note that neither of these integrals converge. And we get the following. We showed that the latter integral diverges. The former integral diverges due to oscillation. And we get the following. Splitting techniques. For limits with infinity, we can split up a finite and infinite part. For integrands with discontinuity at c on an interval where a is less than c less than b, we can split up the interval as long as the integrals are convergent. Single variable calculus, series, convergence and divergence. In terms of pacing, this is 15 out of 18. Sequences and series. The goal of this whole series section is to approximate values of functions by approximating those functions as polynomials. Since a polynomial is a sum of terms of x with non-negative integer exponents, we can think of a polynomial as a sum of powers. In this way, a polynomial of degree n is Pn of x equals this. For example, a quadratic is P2 of x equals this. This summation is also called a series that adds up an ordered list of terms, and this ordered list is called a sequence. A lot of ideas of limits for functions can be analogously applied to sequences, since sequences can be thought of as a function that only take positive integer values as arguments. But be careful. The functions are the gray curves, while the sequences are black dots. On the left, the function 1 over x and the sequence 1 over n have the same limit of 0 as they go off to infinity, On the right, the function cosine 2 pi x does not have a limit at infinity due to oscillations, but the sequence cosine 2 pi n has a limit of 1. Sequence a1, a2, a3, and so on. Above, an infinite sequence is an ordered list of terms, and the entire sequence is denoted by a1, a2, and so on, equals an, equals this, where n element of positive integers. Note that a set is a collection of objects where order is not important. A sequence an has the limit L in R, and we write limit n to infinity an equals L, or an to L as n to infinity. If limit n to infinity an exists, we say the sequence converges or is convergent. Otherwise, we say the sequence diverges or is divergent. We can diverge by going to positive or negative infinity, by oscillating, etc. Series n equals 1 to infinity an equals a1 plus a2 plus a3 plus and so on. Above, an infinite series is the sum of terms of an infinite sequence. The nth partial sum of a series is Sn equals this. If the sequence of partial sums Sn converges, and limit n to infinity Sn equals S exists as a real number, then the series An converges. Otherwise, if sequence Sn diverges, then series An diverges. When series An equals S, the number S is called the sum of the series. For convergent series An and Bn, these are also convergent. This and that. A convergent and convergent series is a convergent series. A convergent and divergent series is divergent series. But divergent and divergent series is inconclusive. Consider these becoming divergent, but these becoming convergent. If this converges, then the full series here also converges. A finite number of terms does not affect the convergence or divergence of an infinite series. The squeeze theorem. If this for that, and these, then limit n to infinity Bn equals L. The monotone convergence theorem. Every bounded monotonic sequence is convergent. A sequence an is bounded if it is bounded above, where an less than or equal to big M, and bounded below, where m less than or equal to an, for all n greater than or equal to 1. Thus, an greater than or equal to m less than or equal to big M. A sequence is monotonic if it is either increasing, if an less than an plus 1, or decreasing, if an greater than an plus 1, for all n greater than or equal to 1. In particular, a sequence that is increasing and bounded above converges, and a sequence that is decreasing and bounded below converges, similar to an asymptote for a function. Telescoping series. A telescoping series has a finite number of terms after cancellation. For example, using partial fractions, we have this. The partial sums eventually yields only two terms, and so S equals limit n to infinity Sn equals 1. Here is a flowchart. Form of a series is more important than a flowchart. Although a flowchart helps organize the tests, the form of a series is the deciding factor in picking which convergence-divergence test to use. Often, you have to manipulate a series into an easier form, or compare it to a series with an easier form. Thus, although the original components of a series might hint at a particular test, you might actually pick a different test after you've done some work. Additionally, even if you found a test that works, there could be other tests that are just as valid. Here is a fact sheet. The divergence test. If limit n to infinity an does not equal 0 or does not exist, then series an diverges. Equivalently, if the series an converges, then limit n to infinity an equals 0. The contrapositive of the implication, if P then Q, is if not Q, then not P. For example, if you have a cat, then you have a pet, becomes if you don't have a pet, then you don't have a cat. The divergence test is inconclusive if limit n to infinity an equals 0. That is, we cannot say anything about the convergence or divergence of the series. Note the problem with saying, if you don't have a cat, then you don't have a pet. One could have a dog as a pet. The geometric series test. For series n equals 0 to infinity ai to the power n, if absolute value r less than 1, then it converges, and its sum is a over 1 minus r. If absolute value r greater than or equal to 1, then it diverges. The partial sum is this. For a divergent case for both the divergence test and the geometric series test, consider series 2 to the power n, where we're always adding something positive and increasing. We have the following. For an inconclusive case for the divergence test and a convergent case of the geometric series test, consider series 1 over 2 to the power n equaling this. We have the following. Geometric series examples. For the sequences r to the power n, where r is a common ratio, we have the following. In summary, limit n to infinity r to the power n equals 0 if r greater than -1 less than 1, 1 if r equal to 1, divergent otherwise. Note how different tests tell different things about sequences or series. And we have the following. The integral test. If series an has an analogous function that is continuous, positive, and decreasing, then the series converges if integral 1 to infinity f of x dx converges, and this series diverges if the integral diverges. Generally, series does not equal integral. For us, we'll use the integral test to prove the upcoming p-series test rather than integrating analogous functions. An inconclusive case of the divergence test is the harmonic series, series 1 over n, since limit n to infinity an equals 0. But now we can prove that it diverges based upon the integral test. Its analogous function is continuous, positive, and decreasing, and its improper integral diverges. Here. Remainder estimate for the integral test. Consider an infinite series S that equals its partial sum, Sn, and remainder, Rn. We have the following. Suppose f of k equals ak, where f is a continuous positive decreasing function for x greater than or equal to n, and series an is convergent. Then we have the following. Here are some pictures. A series ending at n has a remainder Rn starting at n plus 1. Note that the area of Rn equals this is between these improper integrals. The p-series test. For a p-series, 1 over n to the power p, if p greater than 1, the series converges. If p less than or equal to 1, then the series diverges. If p equals 1, then it's the harmonic series. The following examples will be useful for the upcoming comparison tests. We have the following. The direct comparison test. For positive series an and bn, if an less than or equal to bn and series bn converges, then an converges. If bn less than or equal to an and series bn diverges, then series an diverges. Usually compare with p-series or geometric series. For a convergent case of the direct comparison test, consider a series that yields terms that are smaller than the terms of a convergent series. We have the following. For a divergent case of the direct comparison test, consider a series that yields terms that are larger than the terms of a divergent series. And we have the following. The limit comparison test. For positive series an and bn, if limit n to infinity an over bn is a positive real number, then either both series converge or both series diverge. Useful for rational functions or radicals, and usually compare with p-series or geometric series. Used for when the direct comparison test results in the wrong inequality, when we're smaller than divergent series or larger than convergent series. Similar to finding asymptotes of rational functions. For a convergent or divergent case of the limit comparison test, consider a series that yields terms that eventually behave like positive constant multiples of the terms of a convergent or divergent series. This series is convergent like that series, and we have the following. This series is divergent like that series, and we have the following. The results are inconclusive when the limits equal infinity or 0 because they could be found from various combinations of convergent and divergent series. Divergent convergents are these, convergent convergents are these, divergent divergents are these. And we have the following. The alternating series test. For a series an that equals -1 to the power of n minus 1 bn, where bn equals absolute value an, if bn plus 1 less than or equal to bn, and limit n to infinity bn equals 0, then the series will converge. A convergent case of the alternating series test is the alternating harmonic series. Here. Note how this and that. Another example is this Note how this and that. A series AN is absolutely convergent if series absolute value AN is convergent. For example, this is absolutely convergent since both this converges and that converges. A series AN is called conditionally convergent if it is convergent but not absolutely convergent. That is, if series AN converges but series absolute value AN diverges. For example, this is conditionally convergent, since this converges, but that diverges. If a series AN is absolutely convergent, then it is also convergent. Thus, you can prove that series AN converges if you can prove that series absolute value AN converges. But if series absolute value AN diverges, then it is inconclusive concerning this convergence or divergence of series AN. For example, this diverges and that converges, while this diverges and that diverges. Alternating series estimation theorem. If this, where bn greater than 0, is the sum of an alternating series that has bn plus 1 less than or equal to bn and limit n to infinity bn equals 0, then we have the following. In Woods, the size of the error is at most the absolute value of the first neglected term. This is because S lies between any two consecutive partial sums, Sn and Sn plus 1. We'll see examples of this when we do Taylor series approximations. The ratio test. For a series AN, if this less than 1, then it is absolutely convergent. If this greater than 1 or infinity, then it is divergent. If this equals 1, the ratio test is inconclusive. Used for fractions where numerator and denominator are different type of multiplication, products, factorials, nth powers, etc. The growth of functions can be helpful from L'Hopital's rule. Ln n grows slower than n to the power p, goes slower than a to the power n, goes slower than n factorial, goes slower than n to the power n. Consider the ratio test to these geometric series. We have this, the series converges. We have that, the series diverges. With geometric series, the ratios between consecutive terms are constant, and so the limits don't do anything. For other series, the ratios between consecutive terms wouldn't be constant, and so the limits do something. For convergent and divergent cases, consider series that yield terms that eventually behave like a convergent or divergent geometric series. This is absolutely convergent, like that, since we have this. This is divergent like that, since we have this. For inconclusive cases, consider how both the divergent, series 1 over n, and the convergent, series 1 over n squared, have this, and that. In general, the ratio test is always inconclusive for rational functions. The root test. For a series AN, if this less than 1, then it is absolutely convergent. If this greater than 1 or infinity, then it is divergent. If this equals 1, the root test is inconclusive. Useful for nth powers. Consider the root test to these geometric series. Here, the series converges. There, the series diverges. With geometric series, the roots are constant, and so the limits don't do anything. For other series, the roots wouldn't be constant, and so the limits do something. For convergent and divergent cases, consider series that yields terms that eventually behave like a convergent or divergent geometric series. This is absolutely convergent like that, since we have the following. This is divergent like that, since we have the following. For inconclusive cases of the root test, consider both the divergent series 1 over n and the convergent series 1 over n squared have this equals 1. We have this, and we have that. In general, the root test is always inconclusive for rational functions. Single variable calculus, series, power series. In terms of pacing, this is 16 out of 18. The power series in x minus a, or the power series centered at a, or a power series about a, is an infinite series of the form here, where x is a variable, cn are coefficients, and a is the center. Here, x minus a to the power 0 equals 1 when x equals a. When x equals a, all of the terms are 0 for n greater than or equal to 1, and so the power series always converges when x equals a. For a power series here, there are only 3 possibilities for the radius of convergence r. There is a positive number r such that the series converges if this and diverges if that. R equals infinity, that is, the series converges for all x. R equals 0, that is, the series converges only when x equals a. The ratio test, or maybe root test, can determine the radius of convergence, but it is inconclusive when x is an endpoint of an interval of convergence. Sometimes the power series could be a geometric series, and so the interval of convergence could be determined by finding when absolute value r less than 1. To get the interval of convergence, which is all the values of x for which the series converges, the endpoints must be checked with another test. There are 3 possibilities. An interval with endpoints a minus r or a plus r that can contain neither, either, or both endpoints here. For this presentation, when we don't know the behavior at the endpoints, the notation will be this, to show that it could be either these. Negative infinity to infinity, that is, the series converges for all x. A, that is, the series converges only when x equals a. Now, let's find the radius and interval of convergence for these series. To find the interval of convergence of series x to the power n, we use the ratio test to find the radius of convergence and then test the endpoints. We have the following. The radius of convergence is r equals 1 and is centered at 0. we need to test the endpoints of x equals -1 and x equals 1. Here. Testing the endpoints of x equals -1 and x equals 1. X equals -1, divergent, oscillation. X equals 1, divergent to infinity. The interval of convergence is the following. To find the interval of convergence for this, we use the ratio test to find the radius of convergence and then test the endpoints. We have the following. The radius of convergence is r equals 1 and is centered at x equals 0. We need to test the endpoints of x equals -1 and x equals 1. And we have the following. Testing the endpoints of x equals -1 and x equals 1, we have this. X equals -1, divergent p-series. X equals 1, convergent alternating series. The interval of convergence is this. To find the interval of convergence for a series 1 over n x to the power n, we use the ratio test to find the radius of convergence and then test the endpoints. We have the following. The radius of convergence is r equals 1 and is centered at 0. We need to test the endpoints of x equals -1 and x equals 1. Testing the endpoints of x equals -1 and x equals 1, we have this. X equals -1, convergent alternating series. X equals 1, divergent p-series. Interval of convergence is the following. To find the interval of convergence for this, we use the ratio test to find the radius of convergence and then test the endpoints. We have the following. The radius of convergence is r equals 1 and is centered at 0. We need to test the endpoints of x equals -1 and x equals 1. And we have this. Testing the endpoints of x equals -1 and x equals 1, we have this. X equals -1, convergent alternating series. X equals 1, convergent p-series. The interval of convergence is this. To find the interval of convergence of this, we use the ratio test to find the radius of convergence and then test the endpoints. We have the following. First, the value of x is a real number. Then the number is multiplied by the limit. So the product will go to 0 for all x. The radius of convergence is infinity, and so the interval of convergence is this. To find the interval convergence of this, we use the ratio test to find the radius of convergence and then test the endpoints. We have the following. First, the value of x is a real number. Then the number is multiplied by the limit. So the product will go to infinity when x doesn't equal 0. The radius of convergence is 0, and so the interval of convergence is 0. Note how subtle the differences are for the interval of convergence. Radius of convergence, interval of convergence, and we have the following. Although all my radii are 1 and centered at 0, it is not the case in practice. For example, series x minus 2 to the power n has a center x equals 2, radius r equals 1, and an interval of convergence 1, 3 exclusive. Then, For series x minus 2 to the power n over 2 to the power n has a center x equals 2, radius r equals 2, and an interval of convergence 0, 4, exclusive. Single variable calculus, series, Taylor and Maclaurin series. In terms of pacing, this is 17 out of 18. Power series can represent a function as well as a function can represent a power series. For example, the geometric series and its sum here for absolute value x less than 1 can represent the function here on the interval -1 to 1 exclusive. Regarding the nth partial sum of series n equals 0 to infinity x to the power n, the approximations for f of x equals 1 over 1 minus x become better as n increases. At x equals 0, we go from the best constant approximation to the best linear approximation to the best quadratic approximation, and so on. And we have the following. As how functions can be differentiated or integrated, we can do the same with power series. Note the following and how we consider the x minus a term. Let f of x equal this, f of x, f prime of x, integral f of x dx. The radii of convergence of both the derivative and integral of the power series are both r. But the interval of convergence can change. For example, consider f of x equals this. The ratio tests show that the ratio of convergence is this, but the interval of convergence is this, this, and this. If f has a power series representation, expansion at a, that is, if this for this, then its coefficients are given by the formula here, which we'll show on the next page. We have the following. Note, for n equals 0, we let 0 factorial equal 1, and f equals the 0th derivative of f, and for all absolute value x minus a less than r. The Taylor series of a function f at a, or about a, or centered at a, is the following. The Maclaurin series, where a equals 0, is the following. The nth degree Taylor polynomial is the following. To find the Maclaurin series, a equals 0, for f of x equals 1 over 1 minus x, we fill this table. If we continue this pattern, we get this generalization. We get the following. Using the formula, we get what we expected, a geometric series, here. Thus, the Maclaurin series for 1 over 1 minus x is this. Since inverse tan x equals this, we can find the Maclaurin series for inverse tangent using substitution and integration. In the integral, when x equals 0, we have inverse tan 0 equals c equals 0. We have the following, and the following, and the following. Since ln 1 plus x equals this, we can find the Maclaurin series for ln 1 plus x using substitution and integration. In the integral, when x equals 0, we have ln 1 plus 0 equals c equals 0. We have the following, and the following, and the following. To find the Maclaurin series, a equals 0, for f of x equals sine x, we fill this table. Note that all even k's are 0, and all odd k's are positive negative 1. If we continue this pattern, then we get this generalization for odd k's. We have the following. Using the formula, we get the following here. Thus, the Maclaurin series for sine x is this. Since cosine equals derivative of sine, we can find the Maclaurin series for cosine using differentiation. And we have the following. Since tangent x equals sine x over cosine x, we can find its Maclaurin series using long division on the next slide. We have the following. By the way, the exact expression for the coefficients is too complicated for this presentation. And here is the long division. To find the Maclaurin series, a equals 0, for f of x equals e to the x, we fill this table. If we continue this pattern, then we get this generalization. Here. Using the formula, we get the following. Here. Thus, the Maclaurin series for e to the x is this. On one hand, we could evaluate functions at a particular x, and, on the other hand, identify sums as functions evaluated at a particular x. For example, this, with x equals 1, becomes this. If we wanted the Taylor series for e to the x at a equals 2, then we would need this. Here, we're lucky, since the derivative is always the same. In other cases, we'd have to find a formula for the nth derivative. We might even need the sum of one series for the even exponents and one series for the odd exponents. Maclaurin series here, where a equals 0. And we have the following. Let's find the first three non-zero terms for the Maclaurin series for sine squared of x. We have the following. We only considered products that would get the x squared term, xx, x to the power 4 term, x times x cubed twice, and x to the power 6 term, x times x to the power 5 twice, and x to the power 3, x to the power 3. Let's find the Maclaurin series for f of x equals this. And we have the following. Single variable calculus, series, error bounds. In terms of pacing, this is 18 out of 18. Since the nth degree polynomial is an approximation, let's see if the error is within a certain maximum error. Error n equals absolute value, remainder n, equals absolute value, function minus approximation n, equals absolute value f of x minus pn, equals absolute value p infinity minus pn, equals absolute value this minus that, equals absolute value this. Let's represent this infinite series as a single term. Before, the n plus 1th derivative was evaluated at a known a. After, it is at an unknown c in a to x exclusive that is hard to find. We have this, and this, and that. Let's replace this hard-to-find term with c with an easier-to-find term. On here, we're replacing this with its maximum. We have the following. Before, we had equal signs for error n. After, it has inequality signs. Lagrange error, Taylor's inequality, Lagrange error bound. Let's show that the second-degree Taylor polynomial for f of x equals cube root x, centered at a equals 8, approximates f of 9 with error less than this. Since n equals 2, we need n plus 1 equals 3, and so fifth derivative of f equals this, and we can note that the maximum value is at x equals 8, since fifth derivative of f is positive and decreasing on interval 8 to 9 inclusive. Thus, we take m equals this. Using the formula, we get error 2 as this. If the Taylor series happens to be an alternating series where bn greater than 0, bn plus 1 less than or equal to bn, and limit n to infinity bn equals 0, then the maximum error of an alternating series is the absolute value of the first omitted term. Error n equals this, and we get the following. Show that the fifth-degree Maclaurin series for f of x equals sine x approximates sine pi over 15 with error less than this. The Maclaurin series for sine of x at this x value satisfies the alternating series estimation theorem, since bn greater than 0, bn plus 1 less than or equal to bn, and limit n to infinity bn equals 0. This becomes that. For this series, which is a fifth-degree polynomial, n equals 2, the first omitted term has 7 as an exponent, n plus 1 equals 3. So, error 5 is the following. And that was single variable calculus. Thanks for watching.